My name is Michael Cunningham. I'm a professor in chemical engineering at Queen's University in Kingston, Canada. And I'm here today with my doctoral student, Raz Abbasi. We're going to describe the work that was done in Raz's most recent manuscript.
Hello, my name is Raz Abbasi, a PhD candidate at Queen's University and a member of Professor Cunningham and Professor Jessup's research group. And I will present a recent publication titled Crosslinking CO2-Switchable Polymers for Paints and Coatings Applications in the RSC Applied Polymer Journal.
I'm going to let Raz do most of the talking during this short presentation because it's her research and she should get the credit. But I'll just make a couple of overview statements on this to provide some background. Professor Philip Jessup and I have been working on CO2 switchable materials and polymers for some years now. These are materials that change their properties dramatically in many cases in response to the presence or absence of carbon dioxide. And a lot of our work has been with CO2 switchable polymers. A few years ago, we started a project looking at CO2 switchable polymers for use in coating applications. And the basic idea was to see if we could replace solvent-based coatings, which emit harmful VOCs, with water-based coatings while we retain the property advantages of solvent-based coatings. So Ross, I'll turn it over to you and you describe your research.
Thanks. So to begin with, applying a protective layer to items significantly extends their durability, reduces the frequent need for their replacement, saves money while also mitigating the overall carbon footprint. Polymeric coatings are mainly in solvent-based or water-based formulation, and the main difference is whether volatile organic compound, or VOC in short, or water is used as a bulk solvent carrier. The solvent-based formulation consists of sufficiently hydrophobic polymer to provide water resistance. As the coating is applied, organic solvent evaporates, allowing polymer chains to form an entangled network, which results to a high-quality durable coating with a high gloss finish. Despite excellent advantages of the solvent-based coatings, the main drawback lies in the significant use of solvent. On the other hand, water-based coatings such as latexes address concerns related to high VOC emissions from solvent-based formulations. This consists of suspension of the polymer particles in an aqueous phase plus some additives. Film formation in this type follows a complex process where individual polymer particle chains gradually coalesce into a coherent film. Water-based coatings, however, perform poorly in some conditions, mainly because of inadequate interparticle diffusion of polymeric chains during the film formation. So, an ideal coating system would combine the performance advantages of solvent-based and the environmental health and safety advantages of water-based coatings. This means having a homogeneous solution of dissolved polymer requiring no VOC or any additives for film formation. Our group has previously developed an aqueous-based zero VOC formulation containing CO2 switchable polymers. These polymers are hydrophilic in presence of CO2, for example in carbonated water, but hydrophobic in absence of CO2. In this study, we focus on enhancing solvent resistance of such a coating through a 1K cross-linking reaction that relies on CO2 switching. To have this 1K cross-linking system, the cross-linking reaction should be inhibited under CO2 while the formulation is storing, what happens during the film formation as CO2 evaporates. To accomplish this goal, possible cross-linking reactions are initially investigated using model compounds that mimic the structure behavior of amine-containing polymers and cross-linking agent in terms of their reactivity in presence and absence of CO2. These reactions were monitored using HNMR and mass spectroscopy, and it was found that the non-bulky tertiary amine reacts quickly with the bromo compound under air, and the reaction is inhibited under CO2, which meet the requirement for having a 1K cross-linking system. The addition of dibromide cross-linking agent to the coating formulation resulted in 99% gel fraction when coatings dried at room temperature. Additionally, the swelling test indicated that the uncross-linked films were soluble in different organic solvents whereas the crosslink film remained intact and insoluble even after 24 hours checking an excess amount of different organic solvents, indicating significant improvement in solvent resistance of coatings after crosslinking. This prototype formulation does not crosslink during storage because the dibromide crosslinking agent cannot react with the protonated amine in presence of CO2, and storing the polymer in the carbonated water solution showed no evidence of formation of higher molecular weight chain polymer. The proposed approach should lead to the development of new environmentally friendly and high-performance coating and contribute significantly to the reduction of VOC emission arising from paints and coatings industry. Furthermore, the cross-linking chemistry that relies on CO2 switching brings a significant advantage to the field of CO2-switchable polymers beyond paints and coatings application. For our future research, we will focus on increasing solid content, and we will also explore CO2-switchable polymers with lower amine content.
Thank you, Raz, and we hope you all enjoyed this short presentation and enjoy reading the manuscript.
Thank you so much. As a result of cross-linking reaction studied by GPC.